Okay, so from where we left off in the last video, yeah, this point. Now, I said something about these guys being in frequency domain. Now, most waves, most signals, most waves are sinusoidal. Sinusoidal meaning they go back, forward, let's say forward, and then backwards. Okay, sinusoids. So they go something like this and this. Most waves. So you see them like this. Okay, most waves like pendulum movements. So since they go like this is a sinusoidal waveform. All right, that's and so it makes sense to have Maxwell's equation in what frequency domain. That's why you see j omega instead of partial t. So we are saying j omega. We made mention of this in the last video, so let's continue from here. Now, with that being said, look at this particular guy we have right here. Okay, this current also has to be in what? In frequency domain. In fact, this guy is in frequency domain. That is why what we have in our note is what? The term Js is what? Is a phasor current. Is a phasor current, meaning current in what? The frequency domain. So yeah, phasor current density. Now current flows in a conductor, right? But this particular current we are talking about is the one on the surface of the conductor or surface of the antenna. So that's how much current do we have on the surface? How much current do we have flowing on the surface of the antenna? That's and of course in frequency domain. How much current do we have in the frequency domain flowing on the surface of the antenna? That current is the what? Phasor current density. So current is a what? Is in amperes, right? Now the surface, okay, the surface we are talking about what? Meters. So amperes per meter. So that's the unit. But I think that wasn't mentioned, so don't worry about that. But just know that this current is the one that's what? Flowing on the surface of the antenna. Okay, now with that being said, when current flows, alternating current, please, alternating current, since the current is alternating, what will happen? It will generate a field. Okay, it will generate a field. Now when it generates the field, and it will generate a magnetic field around it. That magnetic field will generate what? Let's just say this is current flowing, right? So current density flowing, right? Js. Let me use a different color so it will. Okay, so this guy generates the electric and what the magnetic field because of that, because it's alternating. So electric and magnetic field is being generated, meaning this guy is what? It is the source of the fields. So our electric field and our magnetic field, both of them are generated because of the movement of this, because of the existence of this, meaning this guy is the what? Source of the fields. Okay, and that's the rest part of this particular statement here, saying that the term Js in 1b, this one, is a phasor current density in the region, of course, region, surface of the antenna, okay? And we treat it as what? Being the source, just like what I explained. Source of what? Source of the fields. Source meaning something you know, okay? Known. Source of the field. Source means something you know, or we can better say it as source means something that other things originate from. Okay, so that's so we'll stop here for this. All right, now looking at this, you can see that there are two equations here, but if you recall what we did in electromagnetic field theory, there are four equations, four Maxwell's equations. So but we have just two here. Now trying to find the electric or calculate the electric and magnetic field from these four equations, in those days, people who tried to do this in those days found it difficult. However, out of the four equations, they found one that's different. That's one that's equal to 0. Okay, so and the others are equal to something like that, but one of the Maxwell's equation is equal to 0. And which is that? That's the divergence of magnetic flux density. Okay, of course we've made a video on this already, so maybe I'll just drop a link on that one so we can check that out later on. But this is it. Now, since this is one of the Maxwell's equation and it is the only one that's equal to 0, it can be compared to a vector identity. Which vector identity? Which vector identity? The one that says the divergence of the coil of any field. Divergence of the coil of what? Any field equals what? Equals 0. Are we following? If the divergence of the coil of any field equals to 0, guys, look at this. This whole thing can then be replaced by this, because this guy is the same as this, right? Divergence equal to 0, 0. This is the only difference. It means that since the divergence of magnetic flux density equals to 0, and the divergence of the coil, this is the coil, okay? Divergence of the coil of any field equal to 0, it means we can say magnetic flux density B is equal to this. So we can then write this is equal to what? This. Are we together? Exactly. So I think I should name these equations. In our notes, this is equation 4. I should name this thing. This is equation 4 in our notes. Okay? So I believe we've seen how we got to equation 4 in our notes. Equation 1 in our notes, this is 1A, 1B. Equation 2 in our notes is this. This is equation 2 in our notes, okay? And this is equation 4 in our notes. Sorry, equation 3 in our notes. And of course, equation 4. I believe that's clear. Now, okay, I believe that's clear. So one thing first, come back to equation 1. Can you see equation 1? Equation 1, A and B. Please remember that this particular thing means exactly what? B. Do we remember that? It means magnetic flux density. This is magnetic flux density. This is magnetic field intensity multiplied by permeability, which is mu, that's mu, okay? Permeability, mu naught. So, I'm almost referring back to those videos again. So please watch those videos we did on electromagnetic field theory too. They will help you. So this guy here means exactly this. That means we can write this equation as what? We can write that equation as what? This equals minus j omega and b. We can write it as that. In fact, that's what we have in our notes. So remove all this and let's take it down. Let's take it down. So we can now write this j omega, we can now write it like this. This equals what? Equals minus j omega b. Not b actually, but magnetic flux density. So this will give us what? Hold on, before we put an equation number there. We've already said that what? This guy equals what? This guy equals what? This, right? So where you have this, just plug this one in. So you now have everything again. Okay, the same thing. And then you have what? This right there. Okay? So this will give us our equation, what? 5. Is that clear? I hope that's clear with us. Then what happens next in our note to give us equation 6 is just to rearrange it so that we now have 0 at this side. So look at it now. You just do what? You write all this. You write all this. Plus j omega, and you have this equals 0. Is that also? We just took all this and brought it to this other side. So that's what we have here. So what happens next? You have the coil of an electric field, right? Then here you have the coil of what? A, which is a potential, okay, vector potential. So what are we going to do? Factor out coil. We have coil here, you have coil here. Factor out the coil. So you now have what? Coil of, oh, you now have what? Coil of, what will be left here? Electric field. Plus, what will be left here? J omega A. So J omega A equals 0. This is equation 6 in our notes. Alright, hope that's clear. So that's how we got to equation 6 in our notes. Oh, hold on. In our notes, this was not numbered as an equation. Okay, in our notes, this is actually equation 2. Okay, equation 3 is what we'll talk about now. Yeah, we'll talk about equation 3. Then this is equation 4, and then 5, and then 6. Now, before we talk about equation 3, note that the topic is what? Vector potentials, potential functions, not function, but functions. And this, guys, this is what? One potential function. In fact, we use it to compare to magnetic flux density, which has to do with magnetic field, right? So it is what? Magnetic vector potential. Vector because it has magnitude and direction. So relating to magnetic field, so it's what? This guy, only this A is magnetic what? Vector potential. Okay, potential meaning it has the ability to, produce something or get something done. So in this case now we're using this to relate to the magnetic flux density, magnetic field. So this is just one of the potential function. Another of the potential function is what makes equation what? 3. And it says what? The coil, using a vector identity, the coil of what? The gradient of a scalar field is equal to what? 0. A scalar field, only magnitude, no direction. How can you be talking about the coil of gradient of a vector field? Okay, and we know gradient is a slope. Slope doesn't have coil. Slope is not rotating. So that means the coil of a slope, which is gradient of a scalar field, is 0. Now, this vector identity is what we use in our note as equation what? 3. Okay? Now, with this being said, look at this thing carefully. Coil of this guy equals 0, right? Now, go to equation. Just look at the equations. What does it look like? This guy, coil of everything here equals 0. Is that not so? Look at our equation 3. Coil of everything here equals 0, right? Meaning you can link it like this, saying this is the same thing as this, because coil of this is 0, coil of this 0. Is that clear? This will now give us equation 7 by saying this is therefore equal to what? This. So let's go and do that. So now we can say that, okay, good. We can say that this equal to, hold on, plus J omega A is equal to what? This, which is what? Gradient of a scalar field. This will now give us equation 7. Good? Nice. So I think we'll stop here for now.